Hello everyone. Liam, thank you for turning on your video. So I warmly welcome everybody to join this event. And yeah, Moin is here, our co-host. Thank you joining today, Moin. And I hope everybody, so you're muted, by the way. So I'm going to hand over microphone to event coordinator, Liam, who is going to take care of the coordinating event. So we are here, me and Moin, to address your concerns in the chat box. Please feel free to drop any issues or questions do you have. So without any delay, I'm going to hand over the microphone to Liam. Liam, go ahead. We are with you now.
Do you want to start, Professor? Do you want to wait for Professor Emil to join us, or should I start presenting?
Yes, I think he's not here yet, right?
Yeah, no, not yet.
Yeah, maybe we can give like a couple of minutes more. So in the meantime, I just wanted to let everybody know that we are recording the event. So hopefully nobody has objection, but we already sent the invitation in the emails. So just want to make sure that, Guillaume, like, are you like holding co-host role right now?
Yes, I think so. Yeah.
Okay, I'm going to add more as well in case of emergency. So Moin, I'm going to change your role to co-host. So you're muted, by the way.
Now I think I am on mute, yeah. Hi everyone,
Okay.
welcome to our event, and thank you very much, Liliana, Master.
You're welcome. So let me check if there is anybody else I can add as a co-host. I don't know, we have people from, not yet. So I think, do you guys know like what is the exact time in Sweden right now? It's like, I think we have
it's 5 hours ahead, yeah.
5 hours ahead, okay. So it's going to, like, it's evening in Sweden.
It's 5 or 6 after now.
Okay. I'm very excited. This is going to be very successful event, and I'm pretty sure there are many people, including myself. We are waiting very much to hear from Professor Emil, who is one of the bright minds in this area. Yeah, I see that people are, yes, are jumping into the group like after 11:50. That's what I was expecting. Still, I don't see Professor Emil, so maybe we can give a couple of more minutes.
Yeah, keep looking for joins.
So from the audiences, like, are you guys like, are you happy with the voice and like your voice quality? So if there is any problem, please let us know in the chat box, or you can like, before joining Professor Emil, you can simply turn on your microphone. So somebody says, don't hear you very well. Okay. Volume is low. Okay, maybe my volume is low, but Liam, can you speak? Maybe like we can check.
Yeah, I can hear perfectly here.
Yeah, I hear both of you very well.
Okay, like maybe like you guys like turn up your volume from the control center a little bit. Maybe that's from your side. There's a problem. Mm. Just very quickly, if you have access your LinkedIn right now, like I would appreciate if you share the like WebEx link right away, so maybe people can join right away from your LinkedIn, because I already did.
Yeah, I can try to post mine.
So I think hopefully we will have authorization to share the recording in public, but we are not so sure right now. So let's keep that question at the end of event, so people, like I see a private message I just received, so let's see what we can do about the recording.
Professor Emil just joined us.
Okay, I'm going to hand over to Guillaume. Welcome, Professor Emil.
Thank you. I hope you can hear me.
Yeah, we can. Thank you very much for
Hello,
joining
sir.
us,
Yes.
Professor. So, Masoud, do you want to wait for a few more minutes until 12 o'clock here? Or do you think you should?
I think you may have like something to say, and Professor Emil maybe would like to introduce a research group or the ongoing research like more precisely before starting the talk. So yeah, I think it's a good idea to start right now.
Okay, perfect. So, hello everyone, and thank you for joining us today. My name is Guilherme, and I'm with the IEEE Young Professionals Montreal section, and together with the IEEE Young Professionals sections from Toronto, Ottawa, and Turkey, and the Institut National de la Recherche Scientifique, we're hosting the seminar Reconfigurable Intelligent Surface, a Signal Processing Perspective, with Professor Emil Johnson. Professor Emil has received his PhD from the KTH Royal Institute of Technology in Sweden in 2011, and held a joint postdoctoral position at the Alcatel-Lucent Chair of Flexible Radio at Supélec, France, and the KTH Royal Institute of Technology from 2012 to 2014. He's currently an associate professor at the Linköping University in Sweden and a visiting professor at the KTH Royal Institute of Technology. Professor Emil has performed research on microcommunications, radio resource allocation, machine learning for communication, and energy efficiency for over 14 years, having published 3 books, filed more than 20 patent applications, published hundreds of journals and conference papers, and participated in the editorial board of multiple IEEE journals, not to mention several prizes and awards. He is dedicated to reproducible research and has made a large amount of simulation code publicly available. He's also co-host of the podcast Wireless Future and has a popular YouTube channel. In his talk, Professor Emil will explain the fundamentals of reconfigurable intelligent surface from a signal processing perspective, describe some recent experimental validations, and discuss the main research challenges that needs to be tackled in the coming years. Before we start, I kindly ask you to keep your mics off to avoid any distraction. We'll host a Q&A section at the end of the talk, so please send us your questions in the chat box, and Professor Emil will address them later. Without further ado, please help me in welcoming Professor Emil Johnson. Professor Emil, thank you very much for joining us today, and please feel free to start.
Should we wait until it's sharp, or if that is the announced time?
Yeah, like maybe we can check. Do you have presenter role right now? I just want to make sure that you have presenter role and you're able to see your screen.
I think I have that. Let me try to share my screen.
Yeah, like pretty clear. Okay.
Seems to be fine, I guess.
Yep, it's working.
It's working. Yeah, we are admitting people inside the room, so feel free. Like it's your call, Professor. So if you wish to start, so we can start. If you wish to wait 1 more minute, so we can wait.
Yeah, I'm just thinking that it's good to not start before until after the announced time, in case you then you lose the introduction and you will be lost for the rest of the talk. But thank you very much for the kind invitation. It's sort of this great opportunity now when people start to get used to being online and having different kind of activities, and that all of a sudden you can make a world tour over over this first half of this year. I think I have given talks at different places on different topics every other week, so sort of part of some kind of ongoing tour. But it's also a nice opportunity to meet people at different locations.
Yeah, and it's also good for us to have access to many researchers around the world and have people like you, which is a very well-known research, and come to virtually to Montreal to discuss with us.
Yeah, and I think IEEE have this both in the Communication Society and the Signal Processing Society that I'm involved in. They have the Distinguished Lecture Series, which is sort of a sponsorship based on the idea that we need to sponsor people's travel expenses in order to go around to all these different places and give talks. But all of a sudden, the expenses are more or less zero because everyone can attend.
Yeah, it's pretty zero. It's a great opportunity for us to have bright minds within pandemic. You know, this is one of the advantages of the pandemic. And anyway, so we are still happy to host bright minds like you in this event, in the similar events as well.
Okay, thank you very much. I'm just talking to make sure that I don't start with the technical content until after it's 12 o'clock, but I could just start anyway. So I'm Emil Björnsson, and I'm in Stockholm right now, where I'm a visiting professor at KTH. But I'm also part-time working at Linköping University in Sweden. I've been working with some of the things that I will be mentioning here, which is one of the 5G technologies that are utilized to give you better signals in 5G networks compared to previous technologies. So I will describe this and how that kind of technology is sort of leading into the type of technologies that this talk will be about as well. I'm just trying to minimize everything like that. Okay, so I think I will get started now. And I get a question in the chat. Will I expect some kind of prior knowledge from the attendees? No, I think the way I try to design this talk is to give you an introduction to a new emerging area, which is called reconfigurable intelligent surfaces. And for those who are familiar with signal processing or signals and systems, there will be certain things there that I think you will recognize from other places, from books or courses they have taken, and there will be some mathematical content that for those who already are familiar with the topic. But I think the idea here is to sort of provide you with some a perspective of what this is and an intuitive understanding of this kind of topic. So what I will be talking about first is an introduction where I will talk about some of the issues that we have in wireless. Why are we still doing research on wireless communications even if we have a technology that is supposed to be rather good already? And that will lead us into what is the role of reconfigurable intelligent surfaces and what it is, and what is the vision of what this kind of technology can be utilized for. And after that, there will be the part where there will be some equations describing how do we model this mathematically, the systems, how do we tune parameters to make wireless as good as possible when we are using this kind of special surfaces, and what are the use cases potentially, and something towards the end about channel estimation. And yeah, these are my sponsors for my research I would like to mention as well. So starting with introduction, I always start with this slide here to give you some numbers, because many wireless researchers, we are like to just normalize away everything that has to do with how big different numbers are. And we also only talk about decibel scales, about signals are this many decibels stronger than noise or things like that. But I think what is important to understand is that what we are using in wireless communication is that we are transmitting radio waves or electromagnetic waves. They move at the speed of light, and they diffuse very quickly at the speed of light over a coverage area. So if you put out a base station antenna somewhere, and it should radiate so that it's reaching, for example, your phone, then the transmitted power will diffuse very quickly over the propagation environment. So if you say that the signal needs to travel a distance d, then one mathematical thing is that the surface area of a sphere with the radius d is 4 pi d square. And inside your phone, there is an antenna that has a certain size, area A. And if you put this one on the sphere at a certain distance d, then it is the fraction between how big your antenna is and the total surface area of the sphere that is determining which fraction of the transmitted power that is being received. And this is known as the freeze propagation formula. And if we put in some numbers here, say that a typical 5G frequency range is 3 gigahertz. At 3 gigahertz, a wavelength is 1 decimeter or 0.1 meter. And a typical size of an antenna might be a quarter of a wavelength times a quarter of a wavelength. We multiply that together, this will give us the size of an antenna. We put it into the formula here. A is equal to, this number. And then you say, oh, okay, but what fraction of the transmitted power will I receive if I'm 1 meter away from the transmitter? Then it turns out that this number here in the denominator is much larger than the one in the numerator. So already at 1 meter distance, you will receive 0.005%. And if you go up to 10 meters, which is, you typically are never closer than 10 meters in wireless communications, you will lose another 2 zeros here because of the square. So at 10 meters, you have 0.00005%. Now it's thought to be more important to consider decibel scales. This represents minus 63 decibels, and we call that the path loss, the loss over the wireless signal. And this essentially means that if you send out 2 million pieces of signal energy, one of them will be received, and the other 2 million minus 1 will be diffused over the propagation environment. So why am I saying this? Well, the reason is that there's only a tiny fraction of the transmitted power that gets received, and that also means that it is the rest of the signal power is out there somewhere in the world. And if we can evolve our technologies to make use of it, we can improve the signal quality a lot in your mobile phone. So how are we typically doing that? Well, the first thing is that my example was based on the idea that the signal are diffusing in all directions equally much. And that is not how we are building wireless today. We are typically using instead that we have a base station, you put it on a mast or on a rooftop, and it's focusing the energy to where we believe the users are going to be, which is not up in the sky, but down to earth. So you have a narrow transmission down to earth, and then we typically let each base station antenna cover 120 degrees. So they're focusing the energy there. And a typical number is that these are so-called 16 dBi antennas. That means that if you're standing right in front of it, you get the 16 dB or 40 times stronger signal than you would get if the signal are propagating in all directions. So this is how we have built, in all directions equally much. So this is how we have built wireless networks for many years. And it's great if you are one of those people who are standing with their phone where you're supposed to be according to the network operator. But if you are instead, like here, behind the wall, then you're not benefiting from the directivity that we are focusing the signal down here. What you need is that the signal should sort of bounce off some building or make it somewhere, somehow, to you as a user. So you're not benefiting from this kind of directivity. So how can we improve the coverage in those kind of situations? Well, what is done in 5G is that we are controlling the transmissions. Instead of having a fixed transmission down to where the user is, we are using a technology called beamforming adaptive beamforming to be able to steer around the directivity over time. So if the users are behind the wall here, well, then we can steer the signal towards this wall. And if it's down here, we can add the focus in there. And we can switch this over time electronically. The next step would be to say, okay, I can steer the signal towards this building here, but then the signal is hitting the building, and depending how the building is rotated, that will determine if the signal is actually making it towards where the user is, or if it will just be reflected to some other location. So what if we could also control what is happening between transmitter and receiver? This is what might be possible to do in 6G, and that is what these reconfigurable intelligent surfaces are going to do. But in order to understand how that works, I will first have a closer look at how we in 5G are focusing signals in an adaptive manner to you wherever you are. And then the same kind of ideas will be utilized, but in order to control how signals get reflected on walls. So here's an example. Say that we have two antennas. These antennas are radiating signals. So the signals are moving away like radio waves in different directions. And at the same time, we are transmitting the same signal here. So first the green signal are transmitted and they are propagating, then the gray one, then the orange one, and they are coming one after the other. This is like the waves are going up and down, and we are considering every wave top, for example. And in this case, then, this means that in certain directions, like in this direction, you will, if you are a receiver, see that the two green ones are coming at the same time, not with different delays. The gray one are coming at the same time, the orange one are coming at the same time, the red one are coming at the same time, and so on. And this is what we call in physics the constructive interference, that when the two waves are coming in phase, with the same time delay, then you will observe a signal that is stronger. It's the same thing as you're seeing out in the ocean, that sometimes you have bigger waves at certain locations than other locations. And this is something you can control here when you transmit the signals. While there are other directions where the signal will always be delayed in such a way that they are cancelling out each other. So constructive interference typically means here that if you have one antenna that is radiating the signal in all directions uniformly, like in this example here, then if you put two antennas next to each other and let them transmit like this, you as the receiver will observe as if you had focused a signal in that particular direction, because the signal are always interacting in a particular way. And this is how we are building these big base station traditional antennas that you see on rooftops. They are containing multiple antennas elements here, sending the same signal in such a way that you are focusing down to earth where people are. But what if we would like to make sure that we can steer around in which direction the signal comes? Well, if you, in this right example here, are delaying the transmission from the right antenna. So we can see that when we are transmitting the green one here, the orange one has been transmitted here. And there was already two like periods here before the green one was transmitted. And by delaying the signal from the right antenna, we can see that there are other locations, namely in this direction here, where the green ones, the gray and the orange one will add up constructively on top of each other. And that is where we will see the directive reception. So if you are transmitting from these two antennas, the same signal, but with different delays in this particular way, what you as a receiver will observe is that if you are in this direction, it's like the signal were focused there. And if you are in other directions, the signal will cancel out each other and you will not observe any strong signal at all. And then there are some weird directions where there also seems to be some cases where they are adding up constructively. So this is how we are building base station antennas nowadays. So traditional antenna is passive, it's focusing the signal down to where the users are supposed to be, while in 5G, we are building arrays of small elements, like 64 antennas is something that is typical in 5G deployments of today. Each of them can be sending any signal as you like. So they are generating the signals individually, and in that way you can delay the signals in any way you like, so that you can transmit with one directivity to one user, another directivity to another user, and so on. And if you're directing signals to users in different directions, that also gives you this possibility to talk to multiple people at the same time in different angular directions. So this is sort of the main thing with 5G so far. You can direct signals in different directions, and you can serve multiple users at the same time, which is very useful since the data traffic is growing with 50% per year. So instead of having to put up more base stations, you just send more beams. Okay, so this is something that is called massive MIMO, and it's based on the idea that you have a collection of antennas at one location, namely the same location as where you are transmitting. But what if we are considering what happens when you have a surface that is reflecting a signal? So if you think about the mirror, what you're used to is that if you're looking yourself in the mirror, well, then the light is bouncing back at you. And if you have a mirror that is you're looking at it from 45 degrees like this, then you know that you can look around the corner with it. And what this really means is that the signals are hitting the surface here, and then it's different rays are hitting different parts of the surface, and it will be reflected downwards. And one way of understanding where the signal will be reflected is known as the Huygens-Frenzel principle, which is based on the idea that you take your surface, you cut it into very small pieces, and for every piece, you view it as being an radiating antenna. So when this ray is hitting the surface, the signal will be like reflected but re-radiated, as if it were an antenna spreading out the signal in all directions. The same thing for the blue one, and you can draw additional rays like this. And you might then be familiar with what is known as Snell's law in physics, that of course the signal should go downwards here. If it comes in with 45 degrees, it should go out with 45 degrees. Why is that? Well, if you have a collection of many small pieces here that are re-radiating the signals, you will get this kind of constructive interference that I was mentioning. And the constructive interference will mean that in the direction where the paths are equally long, the red path, if you measured it here, and the blue path, if you measure it here, they are equally long. And for that reason, we will have constructive interference downwards here. And that is what you are known to see in physics, that the signal will be directed towards this direction. And if you have an infinite large mirror, everything gets perfect as you are expecting from physics classes. If the mirror is of limited size, there will be more like a beam in this direction. And the reason to consider this Huygens principle instead of just talking about the Snell's law that you have seen in physics is that if you have a surface which is not flat, well, then this principle becomes very useful. So if you have like a mirror here that is curved, then you take the mirror, you divide into small pieces. Every piece is re-radiating the signal in all directions. And then to figure out where the signal gets focused, you need to measure with a ruler here to figure out, okay, the red signal, this path here is equal long as the blue path here. And for that reason, the signal will be focused at this location. So with the curved mirror, we can focus signals. And that is what we are using in satellite receivers, where you have seen this parabolic shape. The signals are coming in from a certain direction, they're hitting the surface, and then it gets focused at this small receiver that is placed in front of the parabolic surface. So in reality, depending on what kind of surface you have, is it flat, is it curved like this, or does it have a more rougher shape? That will determine, based on this Huygens-Frenzel principle, what happens with the radio waves. And can we do something like this, taking the signal after hitting a surface and focus it at one point, particularly a mobile phone, without actually having to bend the surface, put up metal surfaces that are bended everywhere, and if you move around, they will have to be rotated and things like that. Can we do this somehow in a synthetic manner? Yes, we can. And that is what reconfigurable intelligent surfaces are about. So here I'm standing in my virtual office. Here is a base station antenna that is trying to transmit to my iPad. And the signal, if it had to go through the wall here, in addition to this computation that I was presenting earlier with all the big path losses, if it has to also go through the wall, even more will be disappearing along the way. There will be a big absorption, like 20 decibels more will disappear. But here is a window. The signal could make it through the window. The problem is that if the signal goes through the window and then hits the wall here, then the wall will determine the structure of the wall where the signal is going. If it's smooth wall, it will just be reflected like Snell's law towards this direction. And I want the signal to be reflected towards me, towards my iPad. What we can do then is to put up a special type of surface that we call reconfigurable intelligent surfaces. Why do we call it like that? Well, surface means that it's a two-dimensional thing. So it's like something you put up on the wall, like a mirror or like a poster or something. Intelligent means that we can change. Reconfigurable means that the properties that a surface having can be changed over time. And intelligent means that we can actually program what should be going on. So in this case, what we would like to do is that the signal goes through the window. It hits the surface, and then somehow we are configuring it so that it's reflecting the signal focused towards me, like a beam focused towards me. It will be almost like if the transmitter was here from the beginning and transmit that with the 5G massive MIMO type of technology towards me, but it's actually just a reflection that is achieving this. So how can we do something like that? Well, the transmitter is sending a signal towards the surface, and if I am the user standing here, then somehow the surface should be reflecting the signal as a beam towards me. And then at the next moment, there might be another user here that will like to have the signal. And there will then be a controller that is changing something within the surface. And what is it that we can change? Well, if you look here, I have divided the surface into small pieces, and every piece I have assigned a color to it. What is that representing? Well, it represents that the surface is divided into small elements. This could be like an antenna, but without the radio behind that is generating a signal. Instead, it's more like a small metal plate that can reflect the signal. But the signal, or the element, is connected to a switch, which is connected to this controller. And what can we control? Well, there is something called the reflection coefficient that is determining what happens when signals get reflected. And this reflection coefficient tells us what will be the amplitude, or more or less what fraction of the signal that is incident will be reflected and what will be absorbed. And then the reflection coefficient also have something called a phase that is telling you what fraction of the signal that comes in is going to be, or how long will the signal stay within the surface before it gets retransmitted, essentially. And that is what these colors here is indicating. There is a variation in the impedance in the different elements. And by changing this impedance, we are changing the amplitude, we are changing the phase. And if we would like to approximate the surface shape, like this bended surface that I was showing earlier, what is really happening is that the different parts there are going to delay the signals in different ways by having different impedances. And we will see in detail how that can be happening. But this is sort of the goal. You put up a surface that has small pieces. They are typically smaller than the wavelengths, like a quarter of a wavelength, like a quarter of a wavelength. Each one of them can delay the signals in different ways so that the signal comes into the surface with one set of delays, which should mean that the signal gets reflected in a particular direction. But then within the surface, we are changing the delays so that all of a sudden the signal gets reflected in different directions, in this case towards user 2. And this concept is something that people have been talking about a lot in recent years. And people have been making up different names for it over the time. In 2012, it was called intelligent walls. In 2018, it was called software-controlled metasurfaces, because metasurfaces or metamaterial is one way of building these things physically. Reconfigurable intelligent surfaces is something that I have been using in this presentation, and I think this is the most famous name this part of the or nowadays. And this paper also received a big IEEE award this year. Reconfigurable AI metasurfaces, intelligent reflecting surfaces, there are a number of different names. In my paper here, we have a whole table with different names that people have been making up over the years. So if you have seen any of these names here, they typically mean the same thing. So what is then the goal? Well, the goal is to make the propagation environment controllable. So if 5G technology is about putting up base stations that can steer beams in different directions, depending on which user you are serving, you can send the signal in different directions. Then that means that we could send a beam towards this building here. But that doesn't mean that the signal that is hitting the building will be reflected towards the users that are behind the building here. But if we put up this additional surface here, we could potentially control the propagation so it actually gets retransmitted towards this location or reflected towards this user. So the goal is to create a controllable propagation environment where we can control pieces of the propagation environment. We can control how they're scattered, and also if the signal gets absorbed or not, or change polarization. There's a lot of other things that can be done as well. And some use cases that we could potentially have. This is the library at Linköping University, and there are different floors with books, shelves. Supposed to put up a base station at the top, and you're supposed to make the signal going into the different floors here. The problem is that there's a lot of structures here that will block part of the signals. So what could we do? Well, if the transmitter is up here, then we could potentially put up some surfaces at different locations. The signal will make it from the top, be reflected into the different floors. Outdoor, it could be someone standing in their apartment and looking out here, and somewhere around here in the city there will be base stations. The problem is that those base stations might not see you, so in that case they cannot steer signal towards you. So what can we do? Well, in addition to having the base stations, we can have surfaces at different buildings that can figure out where you are and help you to get the signal from the base station into the room where you are. So in both of these cases, sort of the use case is to improve the coverage. And why is that of interest? Well, you probably have noticed already that wireless communication work terrific in the best case scenarios. Then you can stream Netflix videos, no problem. But the problem is when the coverage isn't good enough, when the service that you are asking for cannot be delivered anymore. And then we need to somehow improve the coverage. And this is one way of doing it. So I will now switch over to some mathematical things to explain to you how we are configuring the surfaces. And then towards the end, I will also tell you how you can figure out where the receiver is. So in the beginning, I assume that we know where the user is or how each communication channel look like, and then we will see how to learn it later on. So we will consider what is known as a narrowband system model, which means that the signals are transmitted over a small frequency band, and it's just a simplification about the channel propagation here. And if you're familiar with wireless communication, you know what it means. Otherwise, don't worry, I will present you with the models that we're utilizing. The base station here is transmitting a signal that is supposed to reach the receiver here. And here I have my surface, which contains many elements. I divide it into small pieces, and every element will do something with the signal if we reflect it with a particular type of delay. Let's now have a look at what could happen in those cases. Well, what happens over a wireless channel, particularly if it's a narrowband channel, is that the signal, when it is transmitted over the air, will lose part of its amplitude. And that was what we talked about in the first example. I represent this here over this link to the element here, element n in the surface, as alpha n, and that is the power loss, and the square root of it is the amplitude loss. And then within the surface, a fraction of the signal will be reflected, and the amplitude loss there is represented by gamma n. And then the signal gets reflected again, and it propagates to the receiver, and it's a further amplitude loss represented by beta n. Then, of course, the radio waves need to propagate over there, and there's delay involved in that. That delay from the transmitter to the surface, I call it tau NA. And A stands just for that I'm using A or alphas to represent this link here. And tau is the time, and N here is just that it has to do with this nth element. Within the surface, there is an additional delay, and that delay is something that we can control. And we'll see in a moment how we can actually do that in reality. So this delay is controllable, while the one over this channel to the surface is not. And from the surface to the receiver, it's the same thing. It's something that's given by how long the distance is. Tau NB is the notation to show here. So the received signal, when you're transmitted from the transmitter to the receiver, will be signals that go through capital N different paths. These are capital N different elements here. Each one of them is a signal that is modeled with these 3 different pieces here. So those get received, here's a summation over them, here's some noise. And I, just for simplicity, say there's a signal transmit, and the amplitude loss over the nth element is alpha n, gamma n, beta n, multiply them together like this, and there's a square root. And then when I talk about narrowband channels, the time delays is turning into phase shifts. So these are complex valued signals. We represent something in the so-called complex baseband. So we're adding up the delays, this delay, and that delay. We add them up like this, and we multiply up with J, which is the complex number, 2 pi fc, that is a carrier frequency. And this is the type of delay that is showing up. And if you have been working with the communication courses in the past, you might know exactly how to compute this type of models. But this is essentially what's happening. The signals get multiplied with different amplitude losses, different phase shifts. We add them up over all of the elements, and then we get the received signal in noise. And now the interesting thing here is that everything is determined by the geometry of the world except this control parameter here, the delay that goes on within the surface. So what is these kind of surfaces? Well, here's an example that some colleague of mine in China have built. It's for the 5.8 gigahertz band, which is a Wi-Fi band. It contains 20 rows and 55 columns of small elements. Each element here is a patch that contains some diodes that we can control, some dielectric substrates. The important thing is not exactly how it's implemented, but the point is that within this surface, there is one impedance value, and there is one impedance value of the air around us, and the so-called reflection coefficient is computed by taking the impedance of the surface here, this element, minus the impedance of the air around us. We divide with the sum of them. And what is then important is that we can actually change the impedance of these elements by changing something. In this case, it's a voltage. We call it the bias voltage. It's something that we can change. And as we are changing it, this reflection coefficient is changing. And here is some result from this paper here. And first it has to do with the phase. And the phase was these phases I was showing before, which has to do with the time delay that it's creating. So I am changing the bias voltage from 0 volt, 4, 7, 11, 19 volt. And what you can see is that we get different curves for these different cases. And if 5.8 gigahertz is the band of interest, there is a small band here of say 10 megahertz that we're using in Wi-Fi. Then we can see that within this band, we will, depending on which of these different bias voltages that we are selecting, we will get different phase shifts like this. And in other bands, there are other phase shifts. So we can control the phase shift, the delay, by changing the bias voltage. And depending on which choice we're getting, here I'm showing the amplitude response, the amplitude loss that we're having depending on which frequency we're at. And we can see that, well, there are some variations as well. And these variations are much smaller. They're all between 0.75 up to 0.95. So in this presentation, I will neglect this. I will assume that these parts here are constant, and I will concentrate on the fact that we can change the delays or change the phase shifts by changing this bias voltage. So what would we then like to do if we can change them? Well, this was the received signal that I was considering before. And when we are considering communication performance, well, the goal is to maximize the performance, and that's typically determined by the signal to noise ratio. So we have the signal term, we have the noise term, and I cannot change the power of the signal or the noise, but I can change this component here. So let's take that component, compute its absolute value square, which is what is showing up when we take the signal power divided with the noise power. And now, within this term here, there is one thing that we can change, namely the phase shift within the surface. So if we're adding up different numbers here, and we are allowed to change the complex phase of numbers, how should we select the phase to make the signal to noise ratio as large as possible? Well, one way of thinking of it is that if we have positive and negative numbers and we add them up, we know that the negative numbers and the positive numbers will partially cancel out each other. So it would be preferable to add up only positive numbers, so we get someplace larger, or only negative numbers. And the same thing applies here when we not only have positive and negative values, but we also have the imaginary numbers, because these are complex numbers. But the main principle, which you can show with Cauchy-Schwarz inequality, is that you will like all of these terms here to have the same phase. If that happens, well, then the phase can be moved in front of the sum, and then we can, with the absolute values, remove it. So then we get this as an upper bound, the summation over the square root of this, the amplitude losses for each of the different elements. And how do we achieve something like that? We would like this term here to be equal for all of the elements, equal to some kind of constant. And since the delay that we can create is something that must be positive, we cannot re-radiate the signal before we have transmitted it. We have to rearrange here and say that tau theta n should be equal to some constant minus tau na minus tau nb. And one way of choosing this constant is to make sure that we are picking the smallest number so that we get a positive number here always. We take the largest tau na, tau nb, this is the largest number, and we put that as the constant here, and then we rearrange, and then this is the minimal delay solution. And suppose alpha n, beta and gamma n, these are the same for all of the elements. In that case, we can drop the index. We will sum up n elements that are the same. We square it, we get n squared, and the square root goes away, and then this is the result that we will have. N is the number of elements, and what this is saying us is that we have as we are adding more elements, we are gathering more energy in our surface, and we also being able to focus the energy when we are reflecting it better and better. So why have I showed you this kind of reflection figures before? Well, if we have a surface like this that is flat and it's a regular surface, the same impedance everywhere, well, then the signal will be reflected in this direction according to Snell's law. But if we have a flat surface and we are changing the delays within the surface, then we can have a flat surface, but it behaves as if it's curved like this. And we can focus the signal as I was describing before, even if it's flat. By changing the impedances, we are creating extra delays in part of the surface and no delays in other parts. In that way, we create this focusing. And as the user is moving around, we can change the shape all the time in order to focus the signal always where the user is. So I saw that someone was asking question, so what will we use something like this for? Well, if we first add a direct path, because there will always be a direct path as well, in addition to reflected signals, well, then I will show you in a moment what this can be used for. If we have a direct path, it also have an amplitude loss, it also have a delay, and now the problem would be to make sure that all of these n+1 paths have the same phase, so we can do the same kind of computation as before. Take away the phases, we get the summation of all of the amplitudes. And in this case, since we cannot control this tau d here, we would like to make sure that to match this phase here with this phase here. So an example, say we have a transmitter that is sending a signal to a receiver, and there is a reconfigurable intelligent surface here. And I assume that these alpha, beta, gamma parameters are the same everywhere. Gamma is equal to 1, alpha is the channel from the transmitter to the RS. It's minus 80 dB in this example. From the RS to the receiver, it's minus 60 dB. These are actually not so bad channels. And when it comes to the direct path from transmitter to receiver, we will consider two cases. It is minus 100 decibel, a bad channel, or minus 80 decibel, which is equally good as this channel. And there are some assumptions around what bandwidth we are using and what is the transmit power, things like that. Here I'm showing the capacity, data rate in megabits per second that we can deliver depending on how many elements that we're having. In case 1, where we have a bad channel from the beginning, we can see that as we're adding more and more elements, the performance is going up all the time, and we can get a large performance improvement by going from 0 to 200 elements. And 200 elements is actually not more than a square meter times a square meter. However, if we have a good channel from the beginning, we start at a much higher point here. We have already a quite good capacity in megabit per second, and adding additional elements to it will not have a big impact. So what is the point here? Well, a reconfigurable intelligent surface is particularly helpful when we have a path from transmitter to receiver that is not so strong. So it's really about extending coverage. In other cases, the additional improvement is not particularly large. And what you can see here is also I have a red curve and I have a blue curve. This is based on the math that I was providing earlier. And in that case, I was able to change my phase on every element infinitely well. And if I restrict myself to only pick 4 of these different lines that I had before, lines that will provide us with phase shifts of minus 90 degree, 0, plus 90 degree, and plus 180 degrees, I get these black curves instead, which is essentially the same thing. So it's not so important that we are able to actually tune every element individually in a big with high certainty. And going back to this setup that I was describing, where there were an actual hardware piece, my colleagues in China was using that hardware in order to make measurements. And on the roof of their research building, they put a transmitter somewhere with a directive antenna in this direction. They put up a copper plate here, 50 meters away, and they had the receive antenna over here. And there are some assumptions about the bandwidth and the carrier frequency and the power, things like that. And if you have a copper plate here, the signal hits the surface, there is a constant impedance, and the signal will be reflected somewhere. And in this case, it's not reflected into the receiver. And they are measuring the signal power at different frequencies. Here is 5.8 gigahertz. And you can see the noise that is going on here. And then you can see that there are some improvements here. This is where the signal is existing over 20 megahertz. So 10 and 10. So the noise is above the signal is above the noise floor, but barely so. If we are replacing this copper plate with the reconfigurable surface that they were creating, what happens then? Well, now we can all of a sudden get a much stronger signal. So if here we had a top value of minus 66 dBm, here it's minus 39 dBm. So this is decibel on milliwatt. So there is an improvement of like 15 decibels or more. So apparently now the surface can reconfigure itself so it reflects the signal into this receive antenna. But the key challenge for building stuff like this is actually to figure out how we should reflect it. We know how to reflect it if we know all of those delays that I was describing, but how can we actually learn something like this? Well, the key challenge is channel estimation. And the problem is really that this reconfigurable surface is blind. It doesn't see anything. It's just like you're holding a mirror in front of you and rotate it in different ways. And you don't see how you should rotate it. Someone needs to tell you, rotate it a bit to the right or a bit to the left or bend it in a particular way. And in the same way, we need to make measurements elsewhere in order to tell the RS what kind of impedance pattern it should have. So the general idea is that you have a transmitter that is sending a known signal, which we call a pilot signal. Then we let the RS circle through different configurations. We have a receiver here, the base station, that is measuring how strong signal did it get for the different configurations. And based on those measurements, it solves some kind of optimization problem to figure out what configuration that we should have and then it feeds back this information to this controller. So this is a general kind of mechanism. Mathematically, what can we do? Well, this was the system model I was having. Direct path, and then there was summation here over all of the reflected paths. And if we take this part here, we can write it in a vector form. Because, you know, if you have an inner product between two vectors, we can write it as a summation over the different elements. So if we are gathering for every element, 1 to n, the things that has to do with our control signals, the gammas and the phase shifts, e to the power minus j 2 pi fc, and here was the phase. We gather those things in a vector like this, and then we are gathering everything else. For each element, we have a path to the surface and from the surface. We put them into two different vectors, we multiply them together element-wise like this. Then we have now a model where the received channel, the received signal, if you transmit some signal x, it will go over the direct channel, I call this h, and then it will be going over the channel, which is the inner product between this part, given by nature, given by the amplitude here and the phase shifts, and this controllable vector here, where we can control the phases. We write this as an inner product between g, which is this vector, and omega, which is this vector. And we can also gather this whole thing here. If we are stacking h and g on top of each other, we can write as 1, and then we have omega underneath it. Then this is the full inner product. Now, x is transmitted signal, w is noise, and z is the received signal when we are transmitting. And n here, I'm sorry, n is not this index here. It's some other kind of time index, which we will use now. So say that we are transmitting a known signal, L times. X is equal to some known number, S, from 1 to L. So n is the time index here. But every time I'm transmitting, I use a different configuration, omega for theta 1 to theta L. And then remember, this was the received signal at time n, like this. And this omega will now be different every time I transmit. If I'm now gathering the received signal at time 1 to L as different columns in a matrix, then this part will be the same. The channel is the same all the time. Every time I transmit, I get a different one here, or it's the same one, but I have a different value here, omega. These are columns in this capital omega matrix. I put it like this here. I transmit the same signal S every time, and I get different noise every time. Let's call this matrix set. Let's call this thing omega tilde, where I've added ones on the first row, and then this is a noise matrix W. Now, the formula looks like this. I have set, I have a vector with containing all of the channels. Here I have the matrix that I have selected. Here I have the pilot signal S that's transmitted, and here I have a noise matrix. From this, I would like to figure out what is this signal channel vector. How can I do that? Well, it's multiplied with a matrix. If this matrix is invertible, I can multiply with the inverse from the right, like this, and I can divide with this, and then what will be left is the channel in this vector, and there will be a noise term left. And if I transmit with the strong enough signal, this S here will make sure that this noise is small enough. And one way of selecting this phase shift here is as a so-called DFT matrix, a discrete Fourier transform matrix. So there is a way of selecting omega in order to make sure that this is invertible and we can do these computations. But in order to do that, if we have capital N elements, we have a matrix here which is n plus 1 in size. So we need to transmit pilots n plus 1 times. So this is an issue that the larger the surface is, the more time we need to spend on learning the channels in order to be able to send the signals in different directions. And this is really where the research is standing now. How can we do this more efficiently? Well, often there's something known as sparsity in this type of channels. So typically you put up these surfaces so that there is a strong path to it, a strong path from it, and in those cases we might not have to estimate the entire vector here. We might know something about it in advance. And there is a lot of research that can be done around that. And in this Chinese setup, what we did was to say that every element can only have one of two states, plus and minus 90 degrees. And then we flipped every column from plus to minus 90 degrees. And we said, we looked at, will this improve things or not? And then we circle through all the columns, then all the rows, or if it was the other way around. And then this essentially means that the signal comes in and we are trying out to sweep it in different directions. And by doing this, we achieve the result that you saw previously. So there are ways of doing this that doesn't require as much effort as sending so many piles I was describing before. Some people, including myself, are trying to make some cases against this technology, that it's not necessarily a good idea to utilize it, even if it's a nice theoretical idea. And I think there are two reasons that one could say that this is not a good technology. One is that there, or in general, the idea is that there are alternative technologies that exist. One thing that would be, if I talk with people in the industry, is they're saying, well, you need to power this device, even if it's not putting in extra signal power. In order to reflect the signal, we need to have the control circuits and everything. And if we need to power it, why not put up an extra base station? And that is a fair point. We need to figure out in which cases it's worth to put up these surfaces compared to extra base stations. A base station, of course, needs even much more power. They need some kind of backhaul infrastructure so you know what data to transmit and things like that. And we also need to, when we get smaller and smaller cells, we need to deal with interference. There is also another type of technology that we can put up at locations in order to improve coverage, namely relays. And these have been around for 100 years. The difference with this technology is that while the surfaces are reflecting things immediately, relays are typically half duplex devices that are listening, processing the signal, and then retransmits. But yeah, there is relaying technology as well, and we need to figure out when these reconfigurable intelligent surfaces are beating relays. I think that the really good use cases for these reconfigurable surfaces are when because they are large, they can be utilized to get rid of some of the big variations that channels have, something known as fading. They can be utilized for new cool things like when you are moving around, you can counteract the Doppler effect. And in general, when things are large, you get something known as macro diversity. If there are objects that are blocking, well, then some parts of the surface might be seeing you, and that can help you to do a lot of nice things. That has to do with sort of getting rid of blockage, increase the rank of channels, and things like that. So in summary, before I start answering all the questions that I've seen popping in here, this is a technology which is about trying to control the propagation environment. 5G technology is about improving the transmitters, particularly the base station, in order to steer signals towards you where you are. While this new technology is about trying to control, well, initially people were saying the entire propagation environment, but rather small parts of the propagation environment, but small parts that are placed at the right locations in order to improve coverage in locations where there is bad coverage. And of course, you can always replace the surface with a big MIMO antenna of the 5G type and do something that is much better. But this is sort of a low-cost solution that you can utilize instead of putting up new base stations. And the characteristics is really the thing that we hope that we can build this with low cost, use much less power, because we are essentially just need power to control the device. And I think it's well suited to improve certain kind of channel properties, and maybe at very high frequencies that we will consider in the future, where we cannot really build the technologies like base stations or relays in a good way. This might be the right choice. And in any case, this is a great research topic in academia, and I was just organizing something called the Signal Processing Cup with 37 different teams with undergrad students that were analyzing how to reconfigure the surfaces in the right way. And I think there's a wealth of algorithms and methods to learn and develop in this area. So with that, I just want to mention I have a podcast called Wireless Future, where you can listen to me and Eric Larson talking about this technology and other technologies. I have a YouTube channel where I also have more videos where I'm talking about this technology. So here are some key references. And yes, I saw there were a long list of questions.
Yeah, thank you very much for joining us, Professor Emil. I do have a lot of questions here coming up, and we will start with the first one, which was actually very close to what I was going to ask. Does IRS requires TDMA scheme, or can it steer multiple beams in the same time to multiple users?
This is a good question. So every element can only have one impedance value. So for that reason, it is sort of a device that is mainly suitable for taking care of one user at a time. But then if you have different surfaces like this at different locations, or you divide it up into different pieces, then you can use different pieces for different users. And yeah, in principle, one could also solve more complicated optimization problems where you try to make sure that two signals are reaching the surface, they get reflected in such a way that they are reaching each other's desired location. So it is possible to do such things, but every element can only have one configuration at a time.
Perfect. How do we decide where to place the RIS?
That is a very good question, and I think the general thing that I have figured out is that I think the only use case where this really makes good sense is where the transmitter and the receiver have a non-obstructed line of sight to the surface. So both the transmitter and receiver sees the surface. And we need to then figure out such locations where it's important enough to improve the coverage. Then who's going to pay for it and all those things, it's hard to know. But I think this is sort of the killer application for it. There must be a line of sight path to and from it, but then no line of sight path between the transmitter and the receiver, because then it's not so useful.
Okay, and does ray tracing techniques help us to determine the place of RIS?
Yeah. Ray tracing, I guess in general, that is something that is very useful for telecom operators to figure out where to put up the surfaces. So that can definitely be utilized. Yeah.
So the next question is very similar to the first one. It's trying to understand how can we exploit the different paths, if that's possible. So how we choose the phase shifters when there are two or more well-separated paths? Are we able to create more than one beam via RIS? So it's very similar to the first question. I don't know if you have anything to add.
Yeah, so I think there's still a lot of research to be done there. I have seen particularly that if there is only one dominant path, you sort of lock into that one and you ignore all the other ones. But if there are two dominant paths, I guess one would like to define some kind of trade-off between them, utilize a little bit of both of them.
Okay, perfect. How IRS figures out where you are?
Yeah, I think that question appeared before the channel estimation was presented. So I hope I answered it by describing the channel estimation procedure. But please, if I didn't, you can ask follow-up questions around that.
Okay, perfect. Who would have the ownership of the IRS? The providers, the company that owns the building?
Yeah, this is a general good question, which is also a more general question when it comes to the development now of 5G. So there is one of the really new things with 5G might be that networks will be also private. So companies can put up base stations using 5G technology instead of Wi-Fi inside of their premises, in mines or another important location where Wi-Fi doesn't provide you with the service quality that you need. And in the same way, then, if we will see now over the next 10 years the development where private companies are putting up base station or to improve their wireless services in their premises, well, then they could also put up this type of services. And I think when it comes to relays, which is this is a new type of relay, that is also something that you can either ask your operator to put up, or you can ask your operator, can I please put up a relay at my house so I can amplify the signal into my home, or in some cases, if you build a tunnel, relays are put up in order to amplify there. So there's a number of different use cases where different people would own or pay for it.
Okay, great. In case of the success of the deployments of IRS, do you think that it will replace massive MIMO since it's cheaper and achieve more benefits? What is the practical solution for channel estimation in IRS with thousands of elements?
So I don't view it even as a competitor to something like massive MIMO, and that is what I tried to convey already with this first slide here, where you're saying like massive MIMO arrays that do beamforming is something you put at transmitter or potential to receiver, while this is something that you put in between. So we need both type of things. Then it might be that at really high frequencies, you can't build a massive MIMO array. And then these IRS surfaces could be placed close to the transmitter and help it to create some kind of IRS. But as was pointed out there, the big issue is the blindness of the surface. That if we put it up in an environment where there's no structure in the propagation environment, well, then it will be very complicated to know how to configure it. So that's also yet another reason why I think that cases with strong line of sight paths to and from the surface is the ideal cases, where even if you have thousands of parameters, there's only 4 angles we need to learn. 2 angles, elevation and azimuth to it, and 2 from it, and then that's it.
And another question that I had, and that's related to what you just told us, can we have multiple RIS deployments in the same network, for example, and how, like, there probably be a trade-off between the channel estimation and the number of IRS, and would that be practical to have multiple IRS?
Practical, I don't know exactly how to even define that, but I think if we go back to sort of the let's see, the models that I was considering here. I mean, I had alpha, beta, and gamma, in particular alpha and beta here as any parameters. Even if I illustrated this as we have a surface containing all other things at one location, these could have been a collection of 10 different surfaces that are making up different parts of the summation here. So one can definitely have a sort of many surfaces or one distributed surface somehow containing multiple subsurfaces. So that is something we can definitely do.
Okay, perfect. Thank you. How backscatter communication is different from IRS communication?
So backscattering communication, I mean, it's closely related type of technology. I think in backscatter, the idea is that you try to inject information into the scattered waves. So here we are selecting the elements here, their impedance values, in order to just reflect the signal as a beam towards the receiver. In backscattering, it's more like you have a radio signal, and then you try to modulate it by changing the impedances or some other properties in such a way that when you receive the radio wave, you can see those variations, and that can then convey information.
Okay. Next questions. What is a convincing use case for IRS, and how can we estimate the channel and control IRS in real time?
Yes, so I still think that finding the convincing use cases is one of the big open questions. So when I was recently publishing the paper, Reconfigure Intelligent Surfaces, 3 myths and 2 critical questions. One of the critical questions was, what is the convincing use case? Because I think this is something that we are still looking to figure out under what situations is this technology better than other technologies. So that is something that we still need more voices heard at. And the other critical question is exactly, can we do real-time channel estimation? I think yes, we can in line of sight scenarios. We can do that. Then what real time really means, maybe not for high mobility situations, but for typical indoor use cases. Yeah, there's even a nice video from I think it's the University of Surrey, and you can find a video on YouTube with their reconfigurable surface.
Okay, thank you. Next question. Thank you, Dr. Mill. I'm wondering, for your consideration about the synchronization, how do you ensure the synchronization between IRS, base station, or IRS and user equipment, especially when the environment has many UA?
Yeah, no, synchronization is always a big issue, I would say. I think and I think synchronization, it becomes particularly an issue when when things are changing over time. But I'm not sure if I would view it as a super big issue here. I think that it's sort of like if this if the user phone here and the base station can synchronize themselves using standard technologies, then as long as they are at fixed locations, well, then there will be some kind of delays that are created within the surface. And whether or not there are time synchronized, for example, it doesn't really matter. Even if the frequency variations are different, it doesn't really matter, because this is view it as having a bended metal plate that we're just synthesizing electronically. It will work even if we don't have a particular type of time synchronization, because this one isn't changing its signal at the carrier frequency rate or something like that. It's just a constant once we have configured it.
Okay. Does IRS reflect the signal without converting it to baseband?
Yes.
And what are the different types of hardware impairments that IRS can experience?
What kind of hardware issues or?
Hardware impairments that IRS experience.
Yes. So one thing that I have assumed in the descriptions here is that every element is independent of the other element. So that's why I was able to sum things up here. One of I think the main hardware impairment that will appear that is breaking this model is that when you are changing the impedance of one element, there is a neutral coupling that will change the impedance of the neighboring elements as well. And that is something that will be more challenging to model in order to get this right. So that is one of the main issues, I would say, in order or the main objections against the modeling that I presented today.
Mm-hmm. Please comment on the reciprocity and calibration.
Hmm?
Any comments on the? Okay. Sorry.
Yeah.
I got the question right.
So reciprocity is typically something that holds. I mean, this is something that comes from, I guess, Maxwell's equation, that the channel in one direction on the other direction will be reciprocal. Then, of course, you can, if you want to, make the surface act as non-reciprocal. If you're transmitting in one direction and then you change the configuration, then all of a sudden it's not behaving in the same way in the opposite direction. But unless you on purpose try to destroy reciprocity, then the channel to transmit and if you reverse the role, it will be the same thing.
Okay. And comment on the calibration.
Yeah, I'm not entirely sure what calibration. I think that goes back to the synchronization that we were talking about earlier, and I don't think that we need to synchronize the RIS in any particular way, because it's not varying anything at the symbol rate. It's just choosing between different configurations, and then once we have set the configuration, it is like a bended metal surface that is constant.
Okay, next question. Is the channel modeling the most important challenge?
I think that right now, channel estimation as such is one of the key is the key key challenge. But what goes into that is definitely the channel estimation. The channel modeling, because the more we can utilize about the environment, the better it will be, or easier it will be for us to configure things. And on the one hand, we need to have good models in order to simulate things in the right way. A lot of early papers in this topic were assuming what we call IID Rayleigh fading, which can never ever appear when you're using these surfaces, because it's something that exists when you have one-dimensional surfaces and not two-dimensional. But apart from that, on the one hand, we need to have accurate models when we are simulating things. On the other hand, when we are trying to develop algorithms, we need to figure out what information about channels do we know. What can we know about the geometry that is realistic to know? If we know that the surface has a certain shape, but then we know that probably elements that are close to each other should have similar impedance values. So there's a lot of things to understand there still.
Okay, perfect. Can we use machine learning or deep learning for IIS channel estimation, and which models would be more suitable for optimal usage?
So I had a paper on, I think it was, now I don't remember at one conference last year, I had a paper where we're using machine learning. So instead of doing the channel estimation first and then trying to configure the surfaces under the assumption that we know the channels perfectly, we try to do the whole thing jointly, and we try to at the same time sort of learn how the propagation environment looked like around the surface, because once you put it up, probably the walls won't be moved, and the user will be at roughly the same location. So yes, that also goes back to the channel modeling. Yes, there will for sure be structure in the channels, and either we are able to model it theoretically, or we can try to learn properties using machine learning.
Could you talk about the resource allocation?
Yeah, I'm not entirely sure what to talk about. So I think that I believe it will be hard to let one surface at one location serve multiple users at the same time. So from a resource allocation perspective, I think what you sort of schedule the surface to do one thing at a time, serve one user at a time, help one at a time, and then I think it's also important to figure out when is it worth spending the time on configuring the surface, and how can we sort of allocate the users, schedule them in such a way that we are not having to re-estimate the channel too often, and do this reconfiguration too often.
Thank you. What are other important challenges on IRS?
So there is a wealth of papers. This is a area where there are new papers coming out all the time. But I think what is really important is to try to make sure to figure out now which of these papers are rooted in real phenomena and which are more mathematical curiosities. So I think going into connecting signal processing algorithms with actual implementations, I think this is very important, and to figure out things like this mutual coupling phenomena, for example, and other and see how it is affecting the system.
Okay, any comment on the upper limit of the performance as n equals very large?
Yeah. So one thing I mean, I'm a massive MIME researcher, and one thing that's very common in many of these fields is to let surfaces, antenna arrays, or in this case, RS surfaces, grow large. But then we should remember that all of the system models that we are utilizing, sorry, channel models, they are assuming that we are in the far field of the arrays. And there's something called a Fraunhofer distance that is sort of telling us when we are in the far field or not. And the larger we make the surface, the further away we need to be from the surface before the models becomes correct. So all of the analysis that are appearing when we are using standard channel models and let the number of elements in an array or an RS go to infinity are wrong, because they might be describing what happens when you have up to 1,000 elements or 10,000 elements, but eventually they're breaking down. And We had a paper last year, I think, where we were trying to explain more precisely what is happening when we have many elements and we let the surface grow large. So I think it's number 4 here. Power scaling laws and near field behaviors are massive moment intelligent reflecting surfaces. And what essentially happens is that the same thing has happened if you happen to have the luxury of having a bathroom with a big mirror, that only a part of it is enough for you. And in the same way, when you build a surface that is too large, so it becomes really fills up your field of view, well, then only a part of it is helpful to deal with your surface if you operate as a mirror. But if you are instead trying to operate as a bended thing, then eventually you can focus the energy at the receiver, and eventually you can capture like everything. All the energy that reaches the surface can be focused towards your device. That's sort of the ideal upper limit.
Okay, thank you. Let me see. How could we ensure the reciprocity of IRS, for example, from base station to IRS to user, and from user to IRS to base station, especially when we consider that IRS should be near to the transmitter?
So as long as you have fixed the configuration, there is one reflection coefficient, and I mean, you're changing the propagation world, which you are by changing the configuration of the surface. But once you have set it to one value, the world must follow the wave equations, and the wave equations are reciprocal. So the reciprocity will hold. There is nothing weird happening there unless you are changing the configuration between the uplink and the downlink.
Okay, how to choose L? What is the minimum L required for channel estimation to ensure invertibility of the omega?
So I think what I was describing here is that if there is no structure, so you would like to learn the entire vector here, then since this vector contains n plus 1 elements, 1 element here, and you have n elements, so 1 channel component for each element, then you need to transmit with L equal to n plus 1. So you need to have all the elements plus the direct path, that is a length for your pilot that you need to transmit, which is a big number. But if you know something about the structure of G here, well, then we can essentially replace the G with the parameters that you want to learn instead. For example, say that we know that every column in our two-dimensional matrix or array should have the same configuration within each column. Well, then you can throw away a lot of elements here. You only keep 1 element per column, and then you only learn those ones. And then you can reduce your L here by a lot. So it's really about injecting the elements or more information into your estimation problem and make it more challenging. But at the end of the day, if you have, say, 5 parameters to estimate, you need 5 linearly independent observations in order to estimate them.
I see. Yeah, I think that's the last question we have here. Thank you for the nice presentation.
Sorry for interruption. It was a very long question. I just texted to Prof. Emil to read it himself. Maybe that would be more convenient to read it himself. It was pretty long, so I just let yeah. Did you receive it, Prof. Emil?
Yeah, I can see now that you have sent it. Just maybe it was sent privately to me, but then also to everyone. So I can read it up here. For the case of grid of beam-spaced pre-coding matrix indicators, G node B sends a downlink CSIRS signal, 1 per antenna port, and the UM measures them with our receive antenna and computes the pre-coding matrix indicator from their interface matrix with the help of SED, blah, blah, blah. This one is transmitted back to G node B to use it for wait for beamforming. My question is it possible to use the common source multi-beam antenna? Each port generates a multi-beam simultaneously along with the code book to differentiate the UL location, assume that the reference signal is set after pre-coding. I'm not sure if I can answer such a specific question now on the fly. What I could say is a few things. See if I can remember what I was thinking while reading this. Yeah, one thing I could point out is that when they were implementing this type of thing, it is actually the same. It didn't add any pilots on top of it. They were running Wi-Fi protocols, and then they used the same kind of signals that were already transmitted over the air in order to estimate the channels. And then they knew that since the transmitter and receiver isn't moving, the channel should stay fixed over time. And then every time they send the signal, they use the received signal strength indicator in order to estimate the strength of the signal, and they change the configuration slowly on the RS and use the existing measurements in order to estimate the channels and figure out what configuration changes that helped out and which doesn't. And I think when it comes to doing this in 5G using this kind of signals that was already were described here, when you're sending some kind of signals like the CSIRS reference signals, then either you keep the RS constant while you're making these transmissions, and then you learn the channels only for one configuration, or you start to change it over time, and then we still get some kind of mismatch of information. So if you have multiple antennas at the transmitter receiver here, in particular if you have it at the transmitter side, then in addition to repeat the same signal here multiple times, you will also have to deal with the fact that you send beams in different directions, and this one is changing in a different direction, and the number of dimensions sort of multiply with each other. So it can, the dimensions can blow up very quickly here as well.
All right, one last question that came up to me here is, can you comment on the standardization of the RS on the 3GPP, for example?
Yes, so I think this is a technology that's definitely in its what we say in the early days of it. So, and I think in general, when it comes to standardization, if this will be utilized in 6G, then it's definitely not a 5G technology. If it will be utilized in 6G, what would potentially happen 5 years from now or so is that when 3GPP starts to look into releases that will be utilized in 6G, well then they will create a study item on this to figure out what are the benefits or not. But I know that there are several of the big companies that have expressed particular interest in this technology. So I'm quite convinced that there will be study items on it in 3GPP. Then whether or not it will be utilized in 6G or in the future is hard to predict. I mean, if you look back 10 years ago, there were a lot of 5G branded things. A typical example is NOMA, or non-orthogonal multiple access. That was supposed 10 years ago to be the big 5G thing, and now we have 5G and NOMA isn't there. It's still a study item. Maybe some small flavor of NOMA will eventually make it into the product, but there are you never know which technologies that fits the standards, which ones make commercial sense, and which one are providing good enough improvements compared to competing technologies.
And another question that came up, do you have any comment on the full duplex enable RS or in frequency or time domain?
So this is essentially a full duplex device in the way that, I mean, if the transmitter, once you have configured it, if the transmitter and the receiver here are full duplex devices, so they can transmit and receive at the same time, then they could sort of transmit via the RS, and the signal will be crossing each other over the air and be received at the same time. So just as a mirror can reflect signals from different directions at the same time, this one can do as well. So it is definitely a full duplex device.
Okay. Some people are asking for the slides. I was wondering if you can share with us and we can send them.
Yeah. Yes. So I don't know if you have a way of sending them out to people. In that case, I can share them with
Yeah, we're
you.
just gonna like initiate the sending for the people, like participants. So yeah,
yes.
we can send them like only those people who participate.
Yeah, sure. So then I will send you the PDF, and then you can distributed to the attendees.
And I
Perfect.
just believe we already have the authorization to share the your video recording in our website and YouTube as well.
Yeah.
Okay.
Okay. Once again, I want to thank you, Professor Emil, for joining us today and for giving us this great presentation. And thank you, everyone that joined us as well.
Yeah, and if you have any further questions that I didn't have time to answer that we missed, please feel free to send me an email and I will do my best to answer them.
Okay, great.
Professor Shahi, I just saw your question. Would you like to give a few comments?
No, I was just going to say hello to Emil. I talked with him for about 1 year, and I'm glad that I saw him today again, virtually, of course, but this is okay. How are you, Emil?
Fine, how are you?
Yeah, fine, thanks. Okay, thank you for the presentation, for the talk. It was nice.
Thank you, everyone, for attending.
Yeah, thanks.
Yeah, Mansour, if I can put a thank you message for Professor Emil.
Yeah, for sure.
Yeah, Professor Emil, I'm a big fan and follower of what you do. Actually, I think your approach of sharing the information, all of these both podcasts and the talks, I think one role model for faculty members to share the knowledge. You deserve a distinguished award for that. I'm Ziad, I'm the Region 7 IEEE Canada Young Professional Chair. And I do really appreciate what you do for young professionals, for the community. And do reach to us if you need, I don't know, a recognition or just a testimonial for what you do. That's really appreciated. So thank you again for sharing your knowledge with us.
Thank you very much for the kind words. And it's nice, since you don't meet people physically these days, it's nice to hear that people are actually watching or listening to the things that you're producing. You can see numbers on YouTube, but it's also like if you put something on YouTube, you might have 1,000 views, but then you look into the details and you see that 5 or 10% watched it to the end. So you want to meet those 5 and 10% of people. And I hope later this year I could actually meet some people at conferences again.
Yes.
Sure, thank you.
Yeah, hopefully we will get rid of this pandemic very soon, and we're going to have opportunity to meet you in person one day.
I hope so.
Okay, thanks, everybody.
Thank you, everybody, and I really appreciate you, Professor Emil, and other faculty members who joined us from Montreal section, including Professor Shahi from Polytechnique de Montréal. And I really appreciate everybody who has any questions. Please reach out, and I will redirect your question. Or you already have a contact address, email address of Professor Emil. We already have a YouTube channel. I'm pretty sure most of the people already have access. So feel free to ask any question if you need any information from our site. Thank you.
Yeah, thanks a lot.
Thank you.
Okay.
Right. Do you want to close the session, Mansour?
Yes. Yeah, once again, I really appreciate Professor Emil's precious time to join us. Hopefully, we are going to reach out very soon for another event. Hopefully, you are interested to continue give the community in Montreal another talk in another topic which falls in your expertise again. I am also a big fan of your YouTube channel. I learned a lot from your YouTube channel, especially in massive MIMO and resource allocation. So that would be maybe another topic that we can reach you out. So hopefully before the pandemic, we would have that opportunity again.
Sure.
Thank you once again.
Thank you for organizing.
Thank you. So yeah, so officially our event is ended. So happy. So enjoy the rest of the day, everybody, and hopefully everybody will get vaccination very soon. And stay safe. Bye-bye.
Bye-bye. Thank you.
Bye-bye.
Bye.
So
So
you wanna close the meeting, Monsieur?
actually, I'm going to stop the